Hello, my name is Dan Williams and I'm the Director of Sales at Equipoise. Our ethos is to make scientifically robust software to supercharge your subsurface decision making. This presentation features Velit, which is a plugin for Schlumberger's Petrel Geoscience platform and is now available on both the Ocean Store and within the DELFI environment. In the pursuit of unravelling the mysteries hidden beneath the Earth's surface, accuracy is paramount. Every decision made in exploration and production, the sites for carbon capture and storage, and the placement of offshore wind turbines hinge on a clear understanding of the subsurface geology. I'd like to thank you for spending the next hour with us, where I'll discuss the importance of incorporating a new methodology to your geoscience workflows. Our cutting-edge toolset enables you to perform Constrained Stochastic Depth Conversion, which will revolutionise the way you approach subsurface analysis by enabling you to automatically generate 1,000 depth scenarios varied around your best technical case model. This methodology transcends traditional deterministic approaches by integrating geological knowledge and statistical analysis, whereby you control the range of variability per layer. Velit transforms uncertainty into opportunity, offering a nuanced perspective of the subsurface landscape. Whether it's optimizing well placement, delineating reservoir boundaries, assessing exploration prospects, or safely positioning geohazards, Velit empowers you to make informed decisions backed by robust geological intelligence. By making a cost-effective investment, you can potentially save millions of dollars versus the cost of a misplaced well, and calculate a highly likely prediction of the gross rock volume of your reservoir. This workflow will thus determine the likely economics of your target prospects and ensure the safety of the teams working on the drilling rigs. As I'm sure you're aware, modern-day pre-stack depth migration volumes, even with the latest full waveform inversion processing techniques, are created to optimize for the best seismic picture and are not optimized for true vertical depth. They also offer only a single model of the subsurface. The question I have to ask you is, can you afford to risk everything, including your reputation, on one model of the subsurface? Velit easily enables you to de-risk your workflow by automatically creating 1,000 constrained models varied around your best technical case model, utilizing a scientifically robust methodology. This provides you with a statistically significant number of gross rock volumetric ranges and an understanding of where your PSDM, or best technical case model, is situated against your P10, P50 and P90 values. You can also compute lever analysis to determine the geological layer most sensitive to the GRV calculations, allowing further constraint to your depth scenarios that you can trust. These models can also be summed together to give you a highly likely understanding of the structural closure of your reservoir. With Velit, you can now supercharge your subsurface decisions and be on target in depth with unparalleled clarity and confidence. After that brief introduction, the presentation outline is as follows. I'll spend a little bit of time discussing data QC, and then the importance of the best technical case model, before focusing the remainder of the presentation on constrained stochastic modelling. And without further ado, let's have a look at data QC. And as I'm sure you're aware, 80% of the project work is in the data preparation. And here we are in Velit. Now, I've deliberately excluded the part of the presentation which surrounds the data loading. The main focus of this presentation is to discuss the highlights of the software, and while data loading is very important, I've decided to exclude it at this time. Suffice to say that the key elements of data that Velit will bring in from Petrel is the time grids, the wells, the formation tops, and the seismic velocities. And we are going to construct a layer cake depth conversion model to describe the velocity changes of the layers accordingly. Now, as part of the data QC, one of the key aspects is to have a look at the data that's come in. And one of the first things that we can do is have a look at the data in 3D. Now, this is to assess whether the auto pickers that are used in Petrel for interpretation have been used appropriately. And as you can see here, there's some picking issues where right at the end of a transect, if the picking was done in this direction, that perhaps there's been an error introduced which is not geologic. In this scenario, what you would do is go back into Petrel, correct the error, and then reload the time grid and replace this third layer with the correctly picked grid. It's important to note here that going through the data loader for this process would take about 30 seconds or so to complete this operation. The next thing you might want to do is QC the wells. So in here we have the model tree, and we can select a number of different wells which we can work through and have a look to see if they are conditioned appropriately. Now this well has been divided into the 4 layers of the project, where the formation top, which you can see on the left hand side, meets the time grid on the right hand side. One important aspect of using Velit, which goes back to the basics really, is that you really want your models to conform with the velocity changes that you see in your wells. Now this data set is a demo data set that's been supplied to us, and as a simple 4-layer model, it excludes some of the key changes in velocity which you'd want to capture in your models. As part of the data QC, you're able to work through the wells, having a look at any wells which may have issues, and these are the sorts of things that you might want to go back into Petrel and condition the data accordingly. For example, creating a synthetic to surface, or encompassing issues where you might have spiky logs with non-geologic velocities, or any missing data. Velit is specifically designed to handle the depth conversion after the data conditioning is completed. So predominantly you will do the data conditioning in Petrel itself and almost work in a circular route to come into Velit to make your assessments as to how the data is now working once it's been conditioned, and perhaps you might identify other outliers in the data or any other bad data which you might need to go back into Petrel and correct. Once you've worked through your wells and you have your logs, your formation tops and your time grids all in good order, a nice QC is the ability to then cross-plot the data, and we can have a look to see if there are then any outliers. So for example, Velit offers you the opportunity to have a look at all of the sonic logs stacked on top of each other just for each layer. And here you can see the blue logs are in the background, the red is the active log, and the grey is a log that is, for example, turned off. At this stage, you may see that you have an identifiable trend with a log or several logs falling away from the main area. This could be bad data. It could be, for example, that a log was loaded into a project in meters when the project is in feet, or vice versa, which is a common mistake that we see. Or it could be indicative of the geology actually being faster and being illuminating the story that your data is trying to tell you. Here you can also QC through the data in different domains. So here we can look at the logs in the depth versus time domain, for example, or you can have a look here in the average velocity versus the time from the sonic log. Again, where you might see a well operating in a strange position on these plots could help you identify some of the issues with the data and enable you to correct it. When you're using Velit, you can use the Advanced tab here, and you can also cross-plot any x-axes versus any y-axes. And with all the data loaded, it means that all of the plots are available straight at the click of a few buttons for you to help you quickly work through and QC the data that you need to work on back in Petrel. Performing the QC is quite iterative, but at a certain point you'll be happy with the way that the data is conditioned and you'll want to start building your best technical case model. The benefit of Velit here is that you can iteratively test many different functions per layer. So now I'll spend a bit of time going back into the software and having a look at all of the cool things that it can do. Velit has been developed for over 20 years now, and we've more recently included the wizard, which provides you an easy-to-use interface for you to drive the software and perform the depth conversion functions per layer. Now, during this section, I'll start off fairly easy and work through some of the more complicated functions in turn. If we start here with a simple graphing method, the software checks that the data is loaded okay, and what you have are a number of different graphing methods that are then explained in the section on the right-hand side. So providing you have an understanding of the language of geophysics, any selection that you make, you should be able to read the corresponding information to make an informed decision on your pick for that layer. Now, Velit allows you to choose a number of different methods and to compare them such that you can iteratively find a best fit for the data that you have in your project. For this model, we'll just start off with looking at a apparent interval velocity versus depth to middle of layer, and you've got the option to show the labels on the graph. Now, for this point, this video is obviously on one screen. If you're working in a two-screen environment, the software is designed so that you can dock the windows and stretch them over multiple displays so that you can have your analysis performed with more screen space. But on here, I'll just minimize these down just to get a bit of a better view for you. Now, when you're looking at this, you're looking at the active well in the window here. So for example, you could open up the well tree, you could select a well, and you could see the well update here. You can see the black dot on the map update here. But when you're looking at the data in the curve display, you're going to be performing your analysis to understand the story that the data is trying to tell you. Now here you can see some of these wells have been grayed out, and that's where I've turned them off using the point edit tool. You can also turn off data in the data tab using the tick boxes accordingly. When you select the data using the point pick, you can click on the data point and it will update the well and the black dot as the active well on the surface map and give you an understanding of where that is situated spatially and what is going on for the given layer. Now, the functions that we're looking at is just for layer 1 for this analysis. Now here you can see that there is a replacement velocity that's been arbitrarily used for the well, and at this point, if you're under time pressure, you can just turn off this data point, perhaps if it's knocking off your overall regression parameter, which is shown on the graph here. If you include this data point, for example, you'll see that it makes quite a significant difference to the regression parameters. Now, in an ideal environment, you'd actually want to go back into Petrel and create a synthetic to surface to encompass this, and therefore remove this artificial value that's been created from this replacement velocity. Now, if, for example, we have a look at another well here, you can see again that this well is missing the entire data for that layer. And again, a replacement velocity has been used, and this value is perhaps arbitrarily high. So again, you can just turn the data off, but it would be better to go back and recondition the data in Petrel. At a certain point, you'll be happy with the analysis and the regression parameter that's been selected for the layer, and you can just press Next on the wizard and have the software work through. Now, what you're seeing on the right-hand side is the value of the difference between the formation top in depth and the depth converted time grid. And in this project, these values are represented in meters. So there's a minus in front of this value, and this value is a positive value. And this relates to the difference of the grid being above or below, representing that the velocities have gone too fast and they need to come back to be slower, or that this amount of depth needs to be added to get down to the formation top. At this point, you can see the residual values in the wells, and you have an option here for error correction. So at this point, you can turn error correction on. You could perform error correction using a simple kriging radius, as you can define like so. Now, the two schools of thought on error correction is that you can perform error correction per layer, and you can round these residuals to 0, or you can not perform any error correction. You can understand your residuals, and these might cancel out as you work from surface to depth. You could then provide an error correction grid for the final target horizon, just to tidy up the grid for the tie at that point. So I will proceed with the second school of thought and not provide any error correction as part of this demonstration. Now, as you press next, the software will update, and I will click on these next buttons just to complete the depth conversion for the first layer. Now, all of the grids are actually stored for the layer within the relevant section. And here in the depth slot, you have this grid computed. And in the XYZ slot, you have the values as the error for the depth errors. Now, for this, what you're able to do is click on this little button here and open up these slots such that you can save using the left click to highlight, right click to select, and you can copy these options into these other layers to save those values. What this means is that you can build up to 12 different functions that you can make your assessments on per layer. Now, just to show you how quick it is to then compute another option, here you can select another function just by working through the relevant options in the wizard. We'll select isopac versus isochron. Again, there would be some time spent on the analysis that you would look at the data in, but assuming that everything is okay and the data is conditioned in good order, you can actually use the software very quickly just by working through the wizard, clicking next, and allowing it to do its job in doing the depth conversion using that function. Now again, I will just click on next, ignoring error correction at this stage, and work through the wizard like so. So at this point, within about 30 seconds to a minute, you have your second function recorded, and in the relevant slot, the depth is then updated, and again, you can copy and paste into these slots. So you're then able to click on these values for the grid and for the discrepancy in the formation top, and with that compute things fairly quickly to get an understanding of how a best fit might be working. Now, just between these two sets, you can see the values of the residuals are perhaps a bit higher, and therefore we'd be in a situation where the first option may be more appropriate to use than the second. Now, as I go through this presentation, we'll have a look at a couple of different options. But one of the key aspects of this in building the best technical case model is the use of our optimize module. Now, our optimize module was developed with Dr. Al-Chalabi, who wrote the book Principles of Seismic Velocities and Time to Depth Conversion, and it contains an algorithm that will obtain the optimum V0 and K value for a given layer that has an increasing velocity trend or decreasing velocity trend with depth. So, for example, if we're looking at a layer like this, this would be where the optimize would be useful to use. Now, I'll just close these windows and run the optimize accordingly. So on here, what I'm going to do now, when the software is ready, is I'll just describe to you how the function can be worked to create a geological propagation of velocity per layer. Now, typically you'd work from the seismic datum, but there may be cases, if you're in deep water, for example, where you don't want the velocities to conform with the surface. You actually want them to conform with the seabed. So Velit enables you to load that data and then select the seabed as the surface, and you would then assign the first layer to have the velocity of water contained within it. Alternatively, you've got the ability to encompass uplift and have the velocities again propagate in accordance with what they look like on the seismic. So if you see your seismic reflections being parallel to the surface or parallel to the base, you can add the P factor to be 0 or 1 respectively. More often than not, you'll actually find that there's some level of decompaction, and that there is the percentage value here that you can adjust to encompass the velocities being propagated within the layer using that factor. In this project, I don't have deep water or any uplift, so I'm just going to work ahead using the seismic datum. Now, when it comes to performing depth conversion, one key aspect is that the velocity depth functions that we looked at previously have an issue when you translate them to the time depth domain. And there can be slight discrepancies in the data that can become significant according to your data. Now I'll just go to a PowerPoint slide just to highlight this before I continue. This slide aims to highlight the discrepancy between the velocity and time domains. If you imagine a straight line regression drawn through a series of data points in the velocity depth domain, if you then translate this into the time depth domain, what you can see here is that the real data as the green line and the straight line model that you've predicted in the velocity depth domain becomes a curve. And there is therefore a discrepancy between the real data and the model that you have used. To understand this discrepancy, at each sample down the data, we can calculate the root mean square time difference to get an overall understanding of just how good a fit our model is. One of the key teachings in Dr. Al-Chalabi's book highlights that the minimum discrepancy does not imply minimum depth error. And if we have a look at these two models on these graphs here, the first on the left-hand side shows the actual data in green, having the model time depth curve being very closely aligned to it, as the model is force-fitted to the data, hence there being a non-zero depth error. On the right-hand side, you can see that the vertical apparent interval velocity has been computed, such that there is a 0 depth error at the well location. What you'll note here is that as the model then moves away from the well, you're then not predicting velocities very accurately at all, and hence you have a poor velocity model. Velit is quite special, therefore, in this case, that it enables you to compute velocity models for a given layer in the time depth domain. And the algorithm that is used does this force-fitting process such that you can have a very robust velocity model even from one well. The benefit of using this technique is that the velocity model is independent of the seismic interpretation. It can estimate a reasonably good result even from only one well. It honours the well velocity data as much as possible. The residual depth errors offer the opportunity to evaluate the difference between the model and reality, and the depth error can be corrected later in different ways. As Dr. Al-Chalabi notes, a velocity model should approximate the velocities of the subsurface and predict velocities away from your known data points. Velit's optimize module can therefore be considered a key component in gaining accuracy in depth as it avoids the common mistake of working in the interval velocity versus depth domain, instead working in the time versus depth domain. The strength of using such an optimizer lies not only in the accuracy of estimating V0K, but mainly in its ability to QC your data and your results in a more meaningful way. Now that you've got both of these graphs in your mind, I'll go back to the software. The fit to well curves method relates to the graph on the left-hand side, where we're going to use the algorithm to force the model to bend to the data in the time domain. The second option, to minimize the residual tie with the well formation tops, is the graph on the right-hand side. But this is only really useful if you have a high density of well data. In looking at the software, what we can see here is that before the optimize is run, the algorithm has determined all of the possible V0K pairs for a given well and determined the best V0K pairing for that well as represented by this dot. Now, all of these are then computed in turn, and when we run the optimize, which just takes a few seconds to run, then these values are then contained within this solution trough, where the best fit for all of the wells is determined by this value here. So the K is determined, as is the V0. And this would be the value that is used to compute the velocity fill per layer. In moving through to the next screen, we also have the option within Optimize to fix K and contour V0. This could be especially useful if you have a phase change across your survey area. So for example, here, if we compute this option, we'll see the values of V0 at each of the well locations in turn. Now you can see in this data set, even from the range of data, that there isn't a phase change here. We're not seeing a strong change in velocities. These are all representing fairly soft rocks. If we were going to carbonates, etc., these might be toward, say, 5,000 meters per second. And this application of this process would then balance out that variation. So you can have both a vertical velocity gradient and a lateral gradient encompassed using this technique. Now, as we don't have this option available in this data set, it's not applicable. I'm going to press next and work through to compute the final depth map. Now on here, you'll notice almost immediately that the values at the well locations of the residuals are reasonably high. And if you imagine your discrepancy as a percentage of depth, you might be able to understand that there's an issue here, that we go from depths of around 500 meters down to about 1,200 meters. So these are too big. If we have a look at this against the well for this project, what we can see if we expand the well display is that at this point here, the velocity model really should be broken up into a separate layer. And what Optimize is doing is trying to fit a regression through this data and therefore computing an answer which is too fast, as this layer has not been broken out. So this is really just been used to highlight the importance of getting your layering right, as the Optimize will do the best job it can with the data it's being given. But you will see here that trying to average too much will not give you the accuracy that you are perhaps looking for. The next thing I'd like to discuss with you is the use of seismic velocities with your project. And in here, we have this seismic velocity calibration wizard that we can use to calibrate the seismic velocities on a per layer basis. Now I'll just run this calibration on the first layer for you to get an understanding of what it does. Now the software permits you to use a single value to compute a scaling factor, and this would compute the Dix scaling and adjust all of the velocities by that single value that you would choose based on your analysis between the wells. You can also compute a single constant from a graph through a regression through the data points, but the most useful option is our grid method. And here what you're able to do is have the software determine the scaling factor that would be appropriate to tie the well velocities to the seismic velocities at each location. So if we just take this well as an example, these velocities would scale by 2.47%, and you can see the grid and the values here, whereby at an arbitrary location, you could say at this point, the values would be scaled at 96.6%. As this grid has been generated, you can see in this data set there are some issues in some of these wells, some bullseyes that stand out. If you were to QC these, you'll see that there's a discrepancy in the data, and this is again something that you would want to fix and have the data conditioned appropriately. Once you have this grid computed, you can then run the correction of the velocities for that layer. So at this point, we can click on Run, and these are then the values after the calibration has been performed. So here at this point, you can see that the velocities are 100.32%. And what this relates to is that there is a slight rounding issue. So you can see that maybe the perfect match was 99.5, for example. And most of these values have got to almost 100% through this calibration. Now this is very important because this lateral scaling factor that you have can then give you a strong confidence in the move or the shift from the processing velocities, which we know aren't optimized for true vertical depth, and in calibrating them to the wells in this grid format, then you will have the ability to leverage them for your work going forward. So you would perform the calibration per layer, running it through each time. And once you've done that, you can then use the seismic velocities in the software for a number of different options. So within here, you could just use the velocities from your volume uncalibrated. You could do a direct depth conversion of those velocities, as you can see here. But typically, as you might be aware, this isn't going to give you the accuracy that calibrating the volume will give you. Now, there are a couple of techniques that we can discuss. The first is if you have fairly flat geology. So here you can generate an interval velocity grid with no depth conversion. And in this process, you've got the ability to then smooth the velocity data that you have within the model. As you can see here, the velocities are contained within the project, decimated and illustrated by these pink dots that you can see across the survey area. Now, once this has computed the grid of these raw velocities, you've got the option for smoothing. So on here, we can apply a simple moving average smoother, or we can use a more advanced multipath smoothing. For the purposes of this demonstration, I'll just use this option as it's a little bit quicker. So with the data being smoothed, we now have this velocity grid contained within the software, and no depth conversion has yet been performed. So within here in the grid slot, we have the stacking interval velocity moving average grid with the radius of 1 kilometer. We can then do a mapping method, and again, just to reiterate, this would be useful for fairly flat geology. And we can map the well vertical apparent interval velocities. Here we'll use kriging, and the first thing that we want to do is make an assessment between the grid that we've just created and the values in the wells. So at this point, we've got the option here to check the regression. So in selecting this, we can see the regression through the data, and we have a reasonable R-squared value such that we can say, okay, the velocities correlate reasonably well, we'll be okay to use them. From this point, you can then generate the grid. What the software is then doing is computing the vertical apparent interval velocity at each well location. And then as you go away from the well locations, it's defaulting to the drift grid that you've just created from your calibrated processing velocities. And that is then the control that you're going to have away from your wells. In using this for the depth function, you can then have a very nice computation of depth where you have lateral velocity gradients but no vertical component. When you get to more complex geology, you might want to encompass pseudo wells, and in so doing, the software enables you to compute pseudo wells at the click of a few buttons. In here, pseudo wells are just a selection option within the wizard, and this is where you can define the amalgamation radius and their spacing. What this radius relates to is a 2 kilometer radius around a specific location where all the velocities will be averaged per sample, and as it does that through the entire sequence of data, it will build a pseudo well accordingly. So through here, in selecting the grid, then in clicking pseudo wells, we can then generate this regular grid across our survey area and augment the number of data points that we have away from our known well control. Now the key thing here is that because we've done the calibration process, we'll have a strong confidence in the use of these values. So if we, for example, have a look at the well in the project and click on a well like so, you can see how the pseudo well has been created through this amalgamation process. Now, while I've done this toward the end of this presentation, you'll be able to see that you'd actually perhaps perform this right at the beginning after your data has been QC'd, such that you can use these pseudo wells for all the other functions and options contained within the software. You can also see that these pseudo wells are showing some of the key velocity breaks, and that the model that we've got as a 4-layer model in this project is perhaps too simple, and this should be a 9-layer model, as you can see in the well logs. Now on here you can see that some of these trends are replicated in other wells, so it's not just a fluke in this location. So as you work through the software, you'll get an understanding now that you can start to build your best technical case model through choosing a number of different functions per layer and working through the software like so to get this computed. Now when you come to then think about what the operation that you've done, all of the clicks that you've taken through the wizard have actually been logged in the console. And what you're able to do is then create a workflow of everything that you've done, which moves us from the wizard interface into the workflow interface. In here, you can make your assessments, and I can just bring up an example I've prepared earlier. Now, you wouldn't have both of these on the canvas at once. You would have the best technical case represented by these 4 boxes on the left-hand side. And one of the key aspects of Velit is that it is fully transparent. There's no black boxes. Every click that you've made through the wizard has been logged. And the workflow system enables you to get the answers of how the software computed its results. So in here, you can drill down deeper and deeper, which can give you invaluable kind of weight of technical evidence as part of a peer review process, for example. The workflow system also provides you the ability to run audit trails. If you come back to a project several months later, you can, for example, see how this has all been worked through. You can distribute these workflows to your team. And if you have a new well come into a project, you can rerun the whole depth conversion incorporating that data just at a click of a button. Now, when you're thinking about the selection of these functions, you might start to question, okay, well, which function may be more stable than another? And this is where the combinations option comes in. Now, in order to compute your best technical case model, you'll iteratively choose several different functions to be able to describe the velocity changes of a given layer. And what combinations does is run an automated blind well test where we turn on and off more and more wells through the process. And here I can just delete the pseudo wells. And we run it through this Gaussian distribution where we progressively drop more wells through more models. Now the process actually takes some time to run, as it will actually do the depth conversion of all of these options. And in here, it can be a little bit time consuming if you select everything that you've run. So really this option is to be used such that you can determine a most stable method from several that you've determined to be better than the rest. What you'll then see is a plot where the functions that you're working with are shown with the color, and the software is showing the value with the well on versus the well off. And here you can make an assessment of how stable a function is using this option. Through here you can see that the functions represented by the blue and red curves are quite unstable in their prediction of velocity as you drop more and more wells through more models, whereas the green and yellow are more stable. And then through the use of the software, you can ultimately determine that the yellow function is the most stable of the options compared. So it's at this point where you would then think, okay, well, I've got to my best technical case model, and I'd like to start thinking about uncertainty associated with that. For the remainder of the presentation, we'll see how constrained stochastic modelling can help revolutionize your subsurface analysis. Now, there are many functions that are contained within the software where the time available to discuss everything that the software does is perhaps too short. For example, there are a number of different methods, such as the salt wedge method, which could be useful, or options like Faust, which describe a nonlinear change of velocity with depth, etc. At this point, I'd just like to take it as read that we have chosen an optimal function per layer, and that we are now happy to proceed to compute the multiple realizations based around our technical case model. So in here, I'll go back to layer 1, and the software remembers where you were last. So in adding the range of variation, it's quite handy because you're able to quickly work through the wizard and tick the relevant boxes to add that. What you can see here is if we tick the multiple realization parameters for the workflow, this box opens where we have control over the range of variation for these techniques. Just to give you an example, what we're doing is providing a range that can fit around the data. So here the confidence interval of 95%, you can adjust that to encompass more or less of the data. And we can then take any regression that falls within these confidence bands, which will give us a unique parameter set, and say, okay, for the first layer, I'd like 1,000 parameters that could be used for this range of variation. Now, as part of this constraint, one of the important elements of Velit is that the way that the randomization is done is that these values are not just pulled arbitrarily. Predominantly, most values will be close to the midpoint, with fewer values being selected further away. Now, when we generate the function and add that to the first layer, we then come through and we are provided with the same choices that we've had through the wizard when computing the best technical case that I've just skipped through fairly quickly. Now, what you'll see here is, again, we're presented with the options for error correction. But if you imagine that we've added the range of variation for the other layers, and this can be used from the Al-Chalabi solution trough in Optimize, just as one example, you get to the final layer, and you might want to add error correction to tidy up your final residual values. So here, let's assume that this is the last event. This would be the optimum that you would choose. Here, in adding the range of values, you're giving a minimum range and a maximum range, which ideally you should base equally around the simple kriging range. You could adjust it to include some bias. So, for example, if you specified 10,000 at the high end, it could give some spatial bias toward the maximum range. At this point, when you add that, then the next option is perhaps the most important, as this is then allowing us to specify the volumetrics for the computation. So in here, on the target horizon, again, imagining this is the last layer, you can select this as active, and you can work this volumetric computation in three different ways. The first is between a top and a base, so you could compute this between two layers. You could use the fill to spill algorithm, and this is where the software enables you to select a seed well, and then from this point it will flood fill any structure under that location until it spills. That will then snap as one model, and then it will compute the process again with a different parameter for that layer, or more importantly, for the whole model. The last option is, if you know the contact surface, then you can compute the spill from that contact point up. So to put it simply, we can work between top down or bottom up. And here we have the ability to constrain the computations by a polygon. We have the map units, and if you are working with a contact surface, then you also have the ability to have the multiple realization parameters have a range of variation to that contact as well. So whichever option you choose, Velit has something in here that will be appropriate for the geology that you're focused on, and you're able to make the informed selection and press next. Now, unlike software which would just provide you with a range of variation based on a percentage variation, we're actually making 1,000 unique models based on a different parameter set per layer. And as such, we're able to compute all of the depth images and grids, any errors, etc., and any of these values, including maps that you might want to produce. Any data can be selected from anything that you've parameterized as part of your best technical case model. Now, it's very important to get those clicks selected as you want them, and perhaps not to select everything, otherwise it might take some time to run, and it would also perhaps eat up more hard drive space. Now, within the software, you're also able to write a note to yourself or to your team, such that you can put some notes in which will be saved within the run file. So if you imagine that you have parameterized the multiple realization range of variation for each layer, we then come to the point where we then want to create a looped workflow. And we can say, okay, let's have 1000 realizations. In selecting this file, you'll save that file, and you can then open this in the workflow module, to which point you would have this computed, and all of that range of variation is recorded in these purple boxes. The volumetrics noted here, any maps, etc. And you can use the batch processing so that you can leverage multiple cores on your CPU to speed along the process much more efficiently. This project that I'm working in here is 40 kilometers by 60 kilometers as an example of the size. I have 8 cores on my laptop, and in running this it took about 4.5 hours as some sort of benchmarking value as to how long it might take to run. Now, obviously, if you have many options or have a very large project, it could take a bit longer, but you're in the range where it's perhaps an overnight operation should encompass most projects. At this point, I will load a model that I have run, and on here we will see the results like so. Now, what you're looking at here is the 1000 models. Each model is represented by one of these black dots, and you can see in the Analyze Info tooltip that that model is number 782. You can then see that the models are grouped in the bins, and the number is listed on the y-axis, with the gross rock volume contained within the reservoir structure listed on the x-axis. Now, the first thing that you'll note here is that you can see your P90, P50 and P10 models. The numbers are also listed to the side of them. But more importantly, you can see where your best technical case model, listed here as M0, is situated against the P50. Now, in this data set, as we've discussed, the layering is quite simple. It's only 4 layers when it should be 9. And I've just selected any parameter to run. So this perhaps is far too optimistic, and what you'd be looking to achieve is an M0 close to the P50 value. This would then give you strong confidence that your model is likely, and also give you extra credibility or weight to your argument that you've taken all of the technical steps to have a very comprehensive model as part of a peer review process. Now, at this point, you then might be looking at the P90 and the P10 values and thinking that perhaps the range of your models is too large for your liking. And what we're then able to do is run lever analysis to understand the sensitivity of all of the layers that have gone into the multiple realizations, such that you can further constrain this for improved accuracy. I'll just quickly pop to a PowerPoint slide here to show the lever analysis tool and how a spider plot can be computed, which encompasses all of the variables that go into the multiple realization run by layer as their prefix, and how that these can be plotted against their volume contribution and their percentile contribution. But more importantly, if we look at the chart data stats, then we can see that it's the F statistic column which shows the sensitivity of the relevant component in the computation. And this describes as you go away from 0, you're more sensitive to change. So in this project, what we're seeing in the 4th layer is that the higher range of variation is hugely sensitive to the overall gross rock volume, whereas within the 4th layer again, the lower range of variation is reasonably sensitive in comparison to the other layers going in there. So what you would be able to do is go back into the wizard, constrain the sensitive layer or layers, and then rerun that through the multiple realizations, so another 4 hours or overnight, and then you'd come back with a range of simulations that you would have strong confidence in. Back in the software then, this weight of data that we've created is what we advocate is essential for determining accuracy within the subsurface and goes far beyond that of one single model. Here, within the data table, You can see all of the parameters that have gone into making every model, and you can sort and filter this table to exclude any realizations that you think are invalid. Here you've got the ability to run an animation where you can see each frame of the animation relates to one of the structural scenarios. And it's quite interesting to watch this to see areas of connectivity within the reservoir, etc. Now at this point, it's important to note that each of the simulations are equally likely. And so while this is interesting, it's not necessarily scientifically robust as other methods. What the software enables you to do is to evaluate a number of different options. So for example, you could do a scatter point of the spill point and see how these accumulations are situated graphically. Here, for example, you might assess these maps on the lower end to see how this reservoir structure looks. The majority of simulations seem to look like this, where you have this accumulation here. And in this project, you can see that this higher range also has this accumulation here. So it would be your job then to have a look for any other data, such as evidence from petrophysics, that indicate whether there is connectivity between these structures, such that you can exclude any data that is contained within the multiple realization run. You can also do a number of other stats, and we can only cover something simple in the remaining time. But here, for example, you can get quite granular. So down to a small number of meters, understanding where the likely location of spill may be for your reservoir structure. Within here, the weight of data enables us to stack all of these models together and generate a probability of closure map, where you can see the color is the percentage. And as you zoom in here, the tooltip where the Z value is listed shows you at each grid node what the likely structural closure is. Now here you can get quite granular and zoom in to get a strong understanding of the likelihood of there being structural closure in any given XYZ coordinate. So you can also use the data table to cut out the simulations at a given value. Here you can also go into more detail and, for example, compute the standard deviation. So you might look at maps in meters where you can understand the range of variability down to, for example, a 5 or 10 meter contour interval. We therefore strongly advocate that you'll be able to achieve unparalleled accuracy and depth through using Velit and this stochastic methodology as part of your analysis of the subsurface. In summary then, whether you're dealing with oil and gas, offshore wind, or sites for carbon capture and storage, you can see how you can use Velit to supercharge your subsurface decision making. We can demonstrate with proven success how the implementation of our Constrained Stochastic Depth Conversion methodology can deliver unprecedented accuracy and depth. This can relate to operational efficiency savings in the tens to hundreds of millions of dollars. We also have the expertise to train your teams to a high standard in the discipline of depth conversion. And if training is something that you'd like to talk to us about, then please get in touch. We'd love to hear from you, and we would welcome the opportunity to work collaboratively with you to maximize the efficacy of implementing this strategy. We have a number of different training courses available that would be suitable for all levels of experience. And if you're evaluating the software, we can also work with you through online meetings such that we can get you into the software more quickly. Thanks for taking the time to watch this video today. And if you have any questions on a technical nature, or you'd like to learn more about the software that's not been covered in the video today, then please contact us on our email at support@equipoisesoftware.com. Thanks again for your time, and I hope you have a great rest of your day.